Okay, so this is a problem we were working on yesterday. Um, One thing I realized today is I don't understand why they show these sums here. I don't know what these sums are for. But it says at the end, write a procedure to add binary integers that takes an as input arrays a and b along with length n and returns array c holding the sum. So like, why do you tell me about little a, b, and c? I guess I don't understand the point. You could use it as a test, maybe. I don't know. Um, so anyway, we went through this thing, and the general idea is like we need to make sure that like we get something from this thing. We wrote this like binary adder that's basically just a fold over this thing. So you'll see like we have this return vector with capacity, and then we just kind of fold over the input array plural in reverse because we have to start from the right side and then go from there. So where we left off last time was we need to test this thing. So let's see if we can find binary addition, like some examples of binary addition. Just give me an example, please. Okay, so here's an example, I guess. And they go over the results, which is this. Perfect. So we'll just use this as an example. So if we run in here, we can start by writing a test called, what did I call this thing? Add binary integers. Add binary integers works. And so we need to have two vectors, A and B. We're going to have 0, 1. Now, this thing has to use this this struct, bit, and well, we really only need bit, I think. We don't really need add bit, but we do need bit, which comes from chapter 2. Hey Gil, how's it going? So we should have chapter 2 in scope. That's what that super thing is doing. So we can just like put this example in here as use bit star, I think. Yeah, so that gives me access to 0 and 1. So then we create a vector of 0, 1, 1, 1, like this. And then we create B, which is 1, 1, 1, 0, like that. Yeah, this is kind of cool, actually. We learned this yesterday. I actually just guessed based on some code that I saw previously, and it happens to work. Okay, so then we can run add binary integers, add binary integers, and we should end up with a C that is 10101. 10101. So that's the idea. I think we pass both A, B, and we need to know the output size, which is just c.len. Let's see if those are the right orders. It's not. So c.len. And then we don't pass them. We just pass them like this. And then the result should be C. Well, it should be some C. Like that. Because it returns an option. Okay, so that's that. Oh, I just realized you probably couldn't see some of that. I apologize. But anyway, I was just writing this test here. So cargo test. Okay, so a bit enum bit needs to have partial eq. I mean, can it just have regular eq? I don't really know what partial eq means. And this needs debug. Okay, so we get none, which is pretty interesting. I think. And it's probably the only way we can get none is that something isn't right here. So n is 5? No, I had it right the first time. I don't know why I removed this. So I think that it's possible that with capacity doesn't work the way I expect it to, or the way I'm hoping it does. I think what we may need to do. Yeah, so you can see it here. With capacity creates a vector with given capacity, but with 0 length. So I think what we need to do is initialize the vector with a certain length and all zeros. Resize with capacity in new in. How do we? Can we not make like a sized vector? I want to push. Like I want to. I guess we could just do like ret equals. So this thing's a range. Maybe we don't even need to iter because it's just a range. You could use a vec macro. Oh, okay. Let's just use that then. Vec 0 n. Like this? How do I find this stuff? Like it's unclear to me how I figure that out. These are traits. But like I don't know where the vec. Hey Chalice. Did you see my message by the way? I sent you a message yesterday. We were finishing up this bit addition thing. So LeClown helped me figure out how to actually write this function because I don't really I've never done this. So I realized this yesterday. I've seen this example before, this bit addition one, and if you were a computer scientist, the bit addition one would probably be relatively easy because you've seen this stuff before. But as a non-computer scientist, I've never done this stuff before. So like I don't even know how to do it, and I haven't learned before. So we're learning yet another thing. But my point is that this isn't necessarily a great example when you don't really know what that is. If you don't provide an example, it can be pretty hard for someone to understand if they've never done it before. Um, but again, the background of most people looking at this book will be CS, so they probably know how to do this. Anyway, I lost my train of thought. Okay, so we learned about this vector notation, but what we want to do is figure out how we can find them. So vector macro Rust. I think that's what I was just looking at. Oh, maybe not. Elem. Okay, so create a vector from a given element and size. Okay, so it's like, yeah, 1, 3 of them. But how do I come across this? That's the part I'm unsure about. Okay, so it looks like this is a function. This is a module. So this blue color or orange color is a module. This is the structure. And then this green is a macro. So that would imply that this green is also some kind of macro. Okay, cool. So, no, thank you. Appreciate you. Okay. Anyway, so I find that kind of strange. Like it's kind of hard to find these things. But maybe they're in the book, and I haven't read the book that carefully yet. So anyway, we were getting an out of bounds error basically on this line right here because we didn't have a fully allocated vector. We only allocated the capacity. So, it doesn't really check out of bounds errors for you. Okay, and then we get a pass. So this works as an example. Cool. So that was like some example. Let's see if we can find a different one. Is there another one in here? Okay, we could add like all of these. Just get the answer. Okay, well, actually, this is problematic because I can't really carry two numbers in my version, so that won't work. But I guess we could just open up a binary calculator and then do calculate, and then just use these. Oh, I already have them. Okay, so let's just copy and paste these three things here. Nope, that's okay. So 1, 0, 1, 0, 1, 0, 1, 0. Right? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Okay, and then for C, we're going to have like one additional element, which is going to be 0. Okay, so this one's 1, 1, 0, 0, 1, 1, 0, 0, like that. And this is going to be 0, 1, 0, 1, 1, 1. Oh, but this is too many numbers, isn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because there's 2 carries. Maybe this will work? Or is this... I don't know. Oh, I should start from the right. So 0, 1, 1, 0, 1, 1, 1, 0, 1. I think like this. Maybe it will still work. I'm actually not sure. It does work. Okay, so we don't have this extra 0. And I don't know if that could ever be 1. Like if you can have a situation where there's 8, 8, and then 10 where the first digit is a 1. Unsure. Maybe that's just like a notation that makes more sense when you're doing like 8-digit numbers or something. So you can't. Okay. Well, good. So then we'll just delete this. Oh, not that. We'll delete this 0 here just for whatever reason. So there's 2 examples and it works. I still find this example kind of strange in general because I don't really understand why they're showing me these 3 things. Like, what purpose does this serve if I'm going to generate this C? I don't know, but I also don't know what A and B represent. Like, to me, they just look like constants. They don't look like anything to me. Or maybe this is its representation in some other format, but since I'm unfamiliar, it like doesn't mean anything to me. Anyway, there we go. Good enough is that we have like an example written down and it's working. So that's cool. And the other thing that's cool is like we got to well, with the help of LeClown, we did it in like a pretty interesting style, I suppose. Using an enum and then like basically a folding structure to carry over information, and then a pretty basic loop that probably could turn into some kind of mappy thing so we don't have to actually do the explicit loop. But essentially this is just a fold, so kind of cool. Okay, so next section is all about analyzing algorithms, and I might write some notes here because this looks like a big section, and this one also looks like a bit of a wall of text. So if you have any questions or you can think of like an exercise or something that we could try, let me know. I'm also gonna try. So if you note, the text is a little different between these. Wait, why isn't this work? There we go. Between these two things, I'm gonna try a lighter pen to see if it makes the text a bit easier to read, or it feels more natural writing. Because this is like, I think it's marker, this marker, and I feel like it's just too thick. So I'm gonna try the ballpoint pen and see if that's any better. We'll see. Okay, so analyzing an algorithm has come to mean predicting the resources that the algorithm requires. That makes sense. So it could be memory, communication bandwidth, energy consumption. Most often, however, you want to measure computational time. If you uh, if you analyze several candidate algorithms for the problem, you can identify the most efficient one. And there may just be one viable candidate, but you can often rule out several inferior algorithms in the process. Okay, so before you can analyze an algorithm, you need a model of the technology that it runs on, including the resources that technology and a way to express that, express their costs. Okay, so most of this book assumes a generic one processor random access machine. Uh, okay, with Okay, so in the RAM model, or in this like computational model, it assumes that each instruction takes the same amount of time as any other instruction, and that each data access using the value of a variable or storing into a variable takes the same amount of time as any other data to access. Okay. Um, which is really not how a computer works, right? In practice. Okay. I so Isitsu, just for reference, I put them all on YouTube. So I released yesterday's stream, or I will release the stream from Sunday, at noon today, GMT, I believe, and I'll put this one up as soon as I can. So the streams are always available on YouTube, and they're like slightly edited. I just remove like gaps or like the beginning and end where I'm not doing anything. So you can catch them there. Okay. Okay. I don't really. So it says, strictly speaking, we should precisely define the instructions of the RAM model and their costs. It says it would be tedious and yield little insight. The RAM model contains instructions commonly found in real computers. The data types in RAM model are integer, floating point, and character. Real computers do not usually have a separate data type for Boolean values. Instead, they often test whether an integer is 0 or non-zero, as in C. Yeah, it says they don't concern themselves with floating point precision, but it can be critical in some applications. We also assume that each word of data has a limit on the number of bits. For example, when working with inputs of size n, we typically assume that integers are represented by c log n bits for some constant c greater than 1. Okay. I'm kind of I'm kind of confused at why we're talking about this, but um, maybe it becomes important here in a second. So it says, real computers contain instructions not listed above, and such instructions represent a gray area in the RAM model. For example, is exponentiation a constant time instruction? In the general case, no. Uh, it says when x and n are general integers, typically takes logarithmic time in n. All right. It says if n is an exact power of 2, however, exponentiation can usually be viewed as a constant time operation. It's, that's interesting. So in most computers, shifting the bits of an integer by one position to the left is equivalent to multiplying by 2. Interesting. Anyway, it says we'll try to avoid such gray areas in the RAM model and treat computing 2 to the nth power as multiplying 2n as constant time operations when the result is small enough to fit in a computer word. Okay. Lastly, it doesn't account for memory hierarchy that is common in contemporary computers. It doesn't model cache nor virtual memory. So several other computational models attempt to account for memory hierarchy effects. Okay. Okay, so basically, like the models that were built or we're using to analyze algorithms are all based on this like fictitious computer that's drastically simplified. And the reason for that is because I guess it makes the analysis easier. And if we were to try and include all of these like memory hierarchy effects and whatever else, it would get a lot more complicated. And maybe that's just like not the point. I think yeah, it says like doing this would be tedious and yield little insight into algorithm design and analysis, if I understood that correctly. Um, so I think that we just kind of like take this as is and we just move forward is my understanding so far. So now it says analysis of insertion sort. So how long does the insertion sort procedure take? One way to tell would be to run it on your computer and time how long it takes to run. It says you would find out how long insertion sort takes to run on your particular computer on that particular input under the particular implementation that you created with the particular compiler or interpreter that you ran with the particular libraries that you linked in, blah, 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 blah. Yeah, and if you run it on the same problem, you might get different results. Yep, we know this. Okay, cool. Instead of a timing run or even several runs, we can determine how long it takes by analyzing the algorithm itself. We'll examine how many times it executes each line of pseudocode and how long each line of pseudocode takes to run. Interesting. That part I think is like sounds kind of weird in my head. How long each line of pseudocode takes to run. I'm guessing that you break everything down into like how many clock cycles it would take or something, and then you just say like it would take this many ops to do something. I'm not sure yet. So we have to come up with a precise but complicated formula for running time. Then we'll distill the important part of the formula using convenient notation that helps us compare running times. Okay. Um, First, let's acknowledge running time depends on input. Okay. We should start writing notes, huh? So running time depends on input size. Sure. That makes perfect sense. We also need to define these terms. Okay, so the best notion for input size depends on the problem being studied. For example, such as sorting or computing discrete Fourier transforms, the most natural measure is the number of items in the input. Input size is the number Okay, that seems pretty reasonable. Sometimes it's more appropriate to describe the size of the input with more than just one number. For example, if the input to an algorithm is a graph, we usually characterize the input size by both the number of vertices and the number of edges. tree may use number maybe I should use actual graph here. Okay. The running time of an algorithm on a particular input is the number of instructions and data accesses executed. Number of instructions plus data accesses executed. Okay. How we account for these costs should be independent of any particular computer, but within the framework of the RAM model. Okay. So let us adopt the following view. A constant amount of time is required to execute each line of our pseudocode. One line might take more or less time than the other line, but we'll assume that each execution of the kth line takes c kth time. Okay, so model. Executing kth line of pseudocode takes tax? Where does that come from? Takes c sub k time. Okay. The viewpoint is in keeping with the RAM model, and it also reflects how the pseudocode would be implemented on most actual computers. Okay. Okay. So it says we're going to use the input size and the statement, and all the statement costs CK. Okay, sorry, just a second. So they're going to show like a picture of this. They're going to expand the while loop. The running time is the sum of the running time for each statement executed. Okay, I'm not going to draw this whole thing, but the basic idea is that for each line, they take a cost, and then how many times that it's run. So like, let's say we had 4 I equals 2 to n. There's basically a cost and a number of times we run the thing. So for this loop, we're saying its cost is going to be c sub 1 because it's basically some constant time to execute this line of pseudocode, and we have to run it n times. Okay, and then it goes through, and we end up with an equation for the insertion sort that looks something like this. T of n equals c1n. That's for the first line. So this is for key. Maybe I should write it in a slightly different way. Hello? Could you erase, please? Hey. So again, this is just like an assignment, and then we hit a while loop. So this is where we start to get more interesting. What's T sub I? Okay. Okay, so let T sub I denote the number of times the while loop is executed for that value of I. Okay. So because we have to we execute this while loop a variable amount of times, so we would need to figure out what T sub I is. Wait, but how would we know T sub I? Wouldn't T sub I be different for each loop? I guess that's the point. Okay, anyway, you get the idea. This is kind of like what we're doing. So let's see. Okay, so in the best case is when the array is already assorted. In this case, each time that line 5 executes, in other words, this line, it's already greater than all the values in the subarray. So the while loop on lines 5 through 7 always exits upon the first test case in line 5. Therefore, we have T sub I equals 1, and the best case is given by basically a bunch of constants multiplied together. So we can express this running time essentially as A times N plus B for constants, and A, B depend on the statement cost CK. And thus, this would be linear. So let me write this a different way. So T sub I represents the number of times the while loop runs if the input is already sorted. T sub I equals 1. So when T sub I equals 1, insertion sort is linear. Okay. In N. But that requires you to have a pre-sorted array. So that's obviously not very helpful if you're doing insertion sort. Okay. So the worst case arises when the array is in reverse order. It starts out in decreasing order. The procedure must compare each element of A sub I with each element in the entire sorted subarray. So basically, T sub I is something like looks like n times n over 2. Sorry, n times n plus 1 over 2, maybe? Anyway, it if you just expand this thing out, you end up getting this so when input is in reverse order that is the worst case and ends up being quadratic in N. Okay, interesting. I'm not going to write this whole equation, but basically you can see that for t sub I, you get, I'm pretty sure that it's, well, that's the summation expanded. So I think it's that sum I equals 2 to n t sub I is equivalent to n plus 1 over 2 minus 1 in the worst case. So you can substitute that into this equation, and then you find basically you have a dependency on a twice. So an squared plus bn plus c. Okay. So worst case and average case analysis are, would people be interested in me actually doing a benchmark for this, like to show that it's quadratic? I think I can do that, but maybe it's not that interesting. Okay. We're almost at like exercises again. So our analysis of insertion sort looked at both the best case and the worst case. The remainder of this book, though, will usually concentrate on finding only the worst case running time. That is the longest time for any input of size n. Why? The worst case running time of an algorithm gives an upper bound on the running time for any input. Yeah. And you can guarantee, if you know that, then you can guarantee the algorithm will never take longer. Okay. And it says for some algorithms, the worst case occurs very often. So use worst case running time when analyzing algorithm. It's an upper bound to the runtime, which is nice. Okay. And then it says the average case okay, so like the chances of you hitting the best case are pretty unlikely. And I think like with this sorting example, that's probably a good one. Like what are the chances of you actually having a pre-sorted array when you like ask to sort an array? Probably never. I guess it could be somewhat sorted or something. Like I have cases of sorting code that I'm using now that are somewhat sorted to begin with. Okay, so it says in some particular cases we'll be interested in the average case. We'll see a technique use of probabilistic analysis applied to various algorithms through the book. Okay. Okay, cool. Order of growth. In order to ease our analysis of insertion sort, we used some simplifying abstractions. We ignored the actual cost of the statement using these constants. The best and worst case equations end up being still pretty unwieldy. All of these constants give us way more information than we actually need. That's why we broke this down into like linear and quadratic, and that was like good enough. Okay. Simplifying abstraction. So rate of growth. Rate of growth or order of growth. Okay. Is the thing that really interests us. Therefore, consider only the leading term of the formula, an squared. So oops, wanted to write an. Okay. Since the lower order terms are relatively insignificant for large values of n, we also ignore the leading term's constant coefficient, since the constant factors are less significant than the rate of growth in determining computational efficiencies. So in a squared n, only consider n squared, basically. Cool. Yeah, it says that factor is by far the most important determining factor for running time. And then it just shows like an example. Okay. So to highlight the order of growth of a running time, we have a special notation that uses theta. Or worst case in insertion sort. Okay. Theta of n squared. Theta n squared. For now, think, I used, yeah, never mind. Think of theta notation as saying roughly proportional to when n is large. So n squared means roughly proportional to n squared when n is large. We'll use theta notation informally in this chapter and define it precisely in chapter 3. We usually consider one algorithm to be more efficient than another if its worst case running time has a lower order of growth. Okay, so it says we have some exercises. I'm guessing none of these are going to require coding, so I'll just do them on the notepad here. So given n cubed over 1,000 plus 100 n squared minus 100 n plus 3, in theta notation, we would just write that. Easy. Okay, so consider sorting n numbers in an array by finding the smallest element of A1n. Okay, I need to write some stuff here. So we have A, 1 to n. Okay, so it says write pseudocode, but I'm gonna write the actual code. This one's called, because I like, we're a coding stream, so let's write code. This is called selection sort. Okay, so we'll write it in this style too. What time is it? Oh, I gotta go actually. So let's just get the. So we're gonna have an A that's gonna be a slice of T. It needs to be mutable. We're not gonna return anything. Hydrate. Can do. How's it going, script? Good morning. So this thing needs these. What is it? Debug. Eek. We need ord and copy. So T has ord plus copy. Then we have an A, and we do this. So that's that. I'm doing a good. We are gonna write a selection sort function. I guess. So if we want to do this in like, I think we have to do this like for I. Do I care about this? I don't think so. I think I just need uh 0 like that. And then we need to find an index with the minimum. So there's probably like but we need that on a vector. Iter tools min. Okay. Okay. That's fair. I wasn't thinking about that being like the problem, but maybe it is. Um okay. So I don't need that. I need pub. Well, actually, it doesn't need to be public. Minimum element, minimum index. This thing needs a T that's ordable. Doesn't need copyable, I don't believe. And we're gonna take a. We don't really need a mutable T this time, but we'll probably take one by reference. And then this thing's gonna return maybe a U size, I guess. But I can't do this right now because I actually have to go to work. But I think that's basically the idea. Is you're gonna say like let min index minimum index a I something like this. And then you're going to say A but we also need a copy of AI. So this is like it's going to be AI. And then we need to take whatever that min index was and stick the swap, I think. Now, this part I don't really... Well, we probably just put a len there. Oh, right. So this should just... Don't I'm not going to have this print a usize. We'll just kind of assume that it's relatively safe. Oh, nice. Sorry, I'm not super familiar with Rust yet. Still learning. But yeah, you want to find the minimum index of the whatever it is to the end. And then maybe we do. Maybe it's fine if this is just option. Otherwise, like, it doesn't really work in some cases. And then here we're just gonna say like match min index sum I. Guess we just don't do anything in that case. Something like this anyway. I don't really know of an obvious case where min index can fail. Yeah, that's a good point. Panic. This probably shouldn't happen. But we need to think about that a bit more. So what do we need to do next time? We need to finish this function. Test this function. And then for this, we need to test this function, I think. Oh, I should do this too. Complete. Okay. So I think that's basically what we're doing next time. And super good call out on the like, we should probably do it by, do this stuff by hand because otherwise I'm not going to think about it as carefully as I should. Let me... Like, it's pretty important that we do this stuff by hand. Otherwise, we're relying on the thing. Or we're relying on somebody else's algorithm. Although, I was thinking, like, does that matter so much? But maybe it does, because I need to be able to analyze the... I need to be able to understand the runtime of both minimum index and selection sort, because you're basically just taking the worst of the two, right? Like, I guess it's possible that this part, or sort of this scaffolding, is O of n or something, but this is O n squared, and so it ends up being O n squared. Yeah, exactly. I just pulled that out of my my head. I don't know that either of them are n squared. But I have a feeling it's n squared. It's something like n squared because minimum index, it's something like n squared. Although there may be a log in here because minimum index, it's not going to go to the end every time. So it's not n squared, I don't think. Well, I guess in the case that it's reversed, you have to go to the end of the list every time. So that would be the worst case. Anyway, we'll talk about this more next time, but